It looks like it's recording.
Okay. Hello, everyone. It is my distinct pleasure today to introduce Dr. Tasha Snow. Tasha is a research associate at the Colorado School of Mines down there in Golden, Colorado. And her research focuses on better understanding high latitude ocean and glacier change and how it will affect our planet. Tasha, of course, was a former student here at University of Colorado under Waleed Abdullahi. She and I, of course, have interacted in many different venues because of that. She's just doing a lot of great research on glaciers and ice sheets and oceans, Greenland. Also very interesting, Tasha is a veteran of the United States Navy. And is passionate about helping others develop more inclusive leadership skills in academia. So with that, Tasha, you have the podium.
Awesome. Thanks, Mark. It's great to chat with all of you today. Feels like I literally just left a few months ago, and it's actually been two and a half years COVID time. So wish I could be in person. I would love to do that at some point. All right, am I sharing the right screen with you?
You are. It says Perry Eyes in the Sky.
Cool. All right. So to get started, I am going to chat a bit about new applications in with thermal infrared imagery and glacier-ocean systems using open cloud infrastructure. And I'll start by giving you a little bit of background on ice-ocean interactions in Antarctica and a little on Greenland. And then I'll get into these new thermal remote sensing techniques that we have and more comprehensive and collaborative ways of applying them than we historically have. Before I get started, I want to recognize all of my collaborators who have participated and contributed to all the work that you'll see today. Across the US and internationally, there's quite a few people, so a large body of work. To get started in the background, I know everyone's very familiar with Antarctica. We're very familiar with the fact that it's important for climate change and sea level rise. Almost all of the melt and ice loss occurring around Antarctica occurs at the outlet glaciers and sea ice shelves shown here in the blues and purples by the relatively fast moving ice that comprises them. And about half of that melt stems from melting from the ocean. So the ocean is super important in Antarctica for ice loss. And the glacier ocean systems that I'll be chatting with you about today, just for a little bit of background, I'm sure most of you are familiar with this. The glacier ice shelf is over here on the left. The water masses that we have in Antarctica are winter water on the top, which is fresh and cold. And below that is circumpolar deep water that's salty and warm. And a lot of the melting that we worry about comes from that circumpolar deep water. Around Greenland, we have analogs to these, which are polar water at the surface and Atlantic water at depth. The way that we think about heat being transported to glaciers often is that warm circumpolar deep water coming in at the base of the ice shelf, right at the grounding line where the ice last meets the ground. That melt is fresh and buoyant, so it rises towards the surface as a plume, and then it exits away from the ice front straight out or parallel to it. And as that plume rises and flows away, it draws more warm water in towards the glacier, so you bring more warm water and melting with this cycle. Now, this ice-ocean interaction process is something that is relatively new to our understanding around Antarctica and really understanding how important it is. So in the late 1970s and early 80s is when we started to really recognize how important West Antarctica was for climate change, that it would be impacted by greenhouse gas effect, that it was the weak underbelly of Antarctica. But at that time, we had very few measurements in Antarctica, very sparse all around Antarctica, and we didn't have a full map of Antarctica at that point. It wasn't until 1997 with the Radarsat Antarctic mapping mission that we finally got that map. So before 1997, the mosaic looked like it does here on top, because Radarsat is a radar that is side looking off to the right, and then because of its orbit, it had a huge gap in the middle of Antarctica, the pole hole that some of you are probably familiar with. And Canada, who owns Radarsat, worked with NASA to rotate this satellite to make it left looking, to map the interior of Antarctica. And so by 2000, we have this map of Antarctica for the first time. So this was only, just 2 decades ago that we really got our first full map of Antarctica. And then a lot of research started to come through about how important the ocean was in terms of melting Antarctica. So rapid bottom melting was widespread around Antarctica, found that in the early 2000s. Work by Ted Scambos, who you all are probably familiar with, looking at Larsen B embayment. Lots of different kinds of studies. We're starting to understand just how rapidly things can change in Antarctica. And then by about 2014, and since then, we've really started to focus more on tipping points, and that we may have gone past some tipping points for some glacier ice shelf systems. But we're really not sure about any of that. I know a lot of you are really familiar with that. So a lot of work has gone into understanding this, but this is just so recent in the work that we've been doing in understanding melting by the ocean in Antarctica. And since then, we've been gathering a lot of data. So in the last decade, especially, this is the International Thwaites Glacier Collaboration is one of these groups that have been gathering a ton of data. This project has been gathering data from the ocean, from the atmosphere, from the ice, to understand how the system really works in its entirety. And there's lots of other projects that have been doing this, but it's really been over the last decade that this has been happening, and it's been creating large data sets that we now need to contend with. But even though we have a lot of data that we've been collecting, our coverage of Antarctica is still relatively sparse around the continental shelf. So this is a picture showing the bathymetry and data measurements that we have around Antarctica. And what I want you to notice here is the light blue area around the coastline is almost not covered at all by red. So we have a lot of places we still need to be able to gather data to really understand what's happening around Antarctica. So since we don't have field observations, one of the ways that we can fill in the gaps is using remote sensing. So this is the NASA constellation. There are a lot of other satellite constellations from other space agencies, and potentially a lot of these can provide us with information about the ocean and ocean heat transport. And so the work that I'm doing is really to understand how we can use remote sensing to detect ocean heat transport towards the ice. And some of the work that I've already done has shown that we can do this reliably with sea surface temperatures in some locations, depending on the oceanography. So this is a project where we used the moderate resolution imaging spectroradiometer sea surface temperatures and showed that we could make a proxy that allowed us to determine surface and subsurface water temperatures in southeastern Greenland back in time throughout the satellite record when we didn't have any instrumentation there. And that was very highly dependent on the oceanography of that area and the transport and circulation that happened there. But we could show that sea surface temperatures could be useful in understanding this. Beyond that, we can also use sea surface temperatures to really understand both spatial extent of ocean circulation and do that at high temporal frequencies to really contribute to the gaps that we have in field observations that are often just snapshots, or they're pinpoints of observations that are a time series in one location. So you can't really get the broad breadth of ocean circulation from them. So this is an image of sea surface temperature, which is the color here, looking down at Helheim Glacier, which is located up here in the middle of the top. And this is sea ice and the coastline of southeastern Greenland. And what you'll be able to see here is with the snapshots or the images that we take from sea surface temperatures, we get a rich data set where we can see at high temporal frequency, ocean circulation, a huge intrusion of warm water towards Helheim Glacier. It crossed 40 kilometers over the course of a few hours, bringing warm water towards the glacier. And this isn't something that we've really captured entirely in field observations. So we get this really rich data set from sea surface temperatures. And we can use it to look at the entire region at the same time and show that these kinds of features are actually occurring simultaneously along the entire coastline, along troughs in southeastern Greenland. And so potentially very important for transporting heat towards the ice, and not something that we've really recognized as being a potential transport or heat transport mechanism until now. So remote sensing is really cool, provides us a lot of new opportunities for studying ice-ocean interactions. So with the rest of this talk, what I'm going to talk to you about is some of the projects we have where we start integrating thermal remote sensing with observational data sets, doing some data fusion. I'll show you how we're doing that, looking at the Antarctic Coastal Current. Then I'll chat with you a bit about how we can add machine learning to start to do some automated feature detection, to look at these plumes that come up from glaciers that are small, tiny scale, spatial scales across Antarctica, and then and automating doing that. And then I'll leave you with where we're kind of going next. So with this big data that we have in ice ocean research, how we can use that in the cloud and with open science principles to really accelerate the science that we're doing. So starting out with the Antarctic Coastal Current work that we have. This project is looking at the seasonal and interannual variability of the Antarctic Coastal Current in the Amundsen Sea. So this is West Antarctica. And the coastal current is really important. We have very little understanding of where the coastal current is around Antarctica. There have been very few measurements. We do know that the coastal current is present along the Antarctic Peninsula and in the Bellingshausen Sea, and potentially around much of Antarctica. We know that it is south of the Antarctic Coastal Current, Antarctic Circumpolar Current. It's fast, it flows to the west, and it carries a lot of meltwater because it flows past all the ice shelves, and it increases in its meltwater transport as it moves towards the west. And we know that it goes all the way to the Ross Sea, where it can impact deep water formation that happens in the Ross Sea. So more meltwater within the coastal current potentially prevents deep water formation in the Ross Sea. So it's important for global ocean circulation because that deep water feeds the entire globe. And on top of that, the variability in the coastal current can affect heat transport towards the ice shelves. As it speeds up, as it moves away from ice fronts or becomes closer to ice fronts, it can change how much heat is transported. So it's super important around Antarctica, and we just really haven't had many places where we've quantitatively observed that it's present, where it's located, and how it varies through time. So in this work, I'm using a bunch of different data sets from the field. We're using shipboard measurements of acoustic Doppler current profiler, which gives us water velocity. We're using the ship CTD, which gives us conductivity, temperature, and depth, which allows us to calculate salinity as well. Ocean glider, seal tag, CTD data all provide the same thing. And then we're using remote sensing from MODIS and from Landsat, one with higher temporal frequency and lower spatial resolution from MODIS. And then Landsat has the lower temporal and higher spatial. So we're fusing those together. And the reason why we think we can use thermal infrared from these satellites is because we can use meltwater potentially as a tracer in many places in Antarctica. So on the left here, I'm showing a map of sea surface temperatures from MODIS, just one month in 2010, to kind of illustrate how this can work. So the blue colors are cooler temperatures. And you'll notice that in a lot of places, these blue colors are located close to the coastline in places where here on the right, this GCM output showing us where it expects the coastal current to be in the Amundsen Sea. These, the blue and the faster current where the coastal current is, those match up really well. You'll notice that works really well up here in the northeast as well as in the south, but might be a little bit more challenging to use in the east there, a little bit lower towards the south. And we expect that this is going to be the case. We can't use thermal everywhere. It needs to have a meltwater tracer. So anywhere that's downstream of an ice shelf that is melting and has a lot of outflow that water will be entrained into the coastal current most likely, and we can track that meltwater within the current as a cooler temperature than the ambient temperatures around it of the ocean. Whereas in some locations, the coastal current may not be present where those outflows are, or there may not be outflows. So this proxy that we're using, thermal infrared, to track the coastal current can only be used in certain locations, and we have to have a decent understanding of the oceanography to be able to predict that. So just to give you a little bit of background or a little bit of understanding of what we gathered from the field observations, this is showing water velocity, where blue is towards the south and red is towards the north. So this is right almost close to the coastline. This is right up against the coastline in these green and blue transects. And we can capture the Antarctic coastal current here at the top. It's in the top 100 to 150 meters. And see that as well slightly further to the south, but potentially into 2 or 3 different branches that move toward the south. So it's more confused, and that's also probably why we have a little bit more mixing and less of a signal of meltwater further south. If we look over by Thwaites Glacier, which is out in the southern portion of the Amundsen Sea, the westward flow is in blue, and we see that right at the surface again. And capture that with velocity. But what you'll notice is these are specific dates captured in 2019. So this really can't tell us about variability. So we need to, we can start to use seal tag data to get at some of the variability from within the water column. So this is showing temperature, salinity, and geostrophic velocity. So it's velocity calculated from water temperature and salinity. And what we notice is that the Antarctic coastal current, the blue flowing to the south, up in the north, is larger, faster, and further offshore in summertime. And this makes sense because in summertime, we have a lot more melt, which helps to accelerate the Antarctic coastal current and make it larger. So we're capturing these things with field observations. Now, what can we do with thermal infrared? So MODIS provides sea surface temperatures as a product, but Landsat doesn't. So I've created a thermal processing pipeline that allows us to capture temperatures. What I'm just showing you here is just going to be looking at thermal gradients. So we don't actually process all the way to sea surface temperatures, but we are doing some work. We are producing an algorithm for that as well for Landsat to get sea surface temperatures. From that, we get some images like what I'm showing here. So the yellow is cool and the red is relatively warm. Thwaites Glacier is down here. We're again in the south. And this is where we saw westward flow in the shipboard measurements that we had. To give you more context, these are the ocean temperatures. These are the icebergs and sea ice that are masked out and cloud. And then the coastal current is this band of cold, relatively cold water flowing against the ice front. And this is just a time series from December 17th to January 9th from 2017. So we can start to get at variability really easily with this thermal data over longer periods of time than we could from shipboard and over many years. So from this, what we can do is we can start to measure in a very basic way the width of the Antarctic coastal current. And that's what I'm showing here. So the coastal current width is across the x-axis. On the y-axis is time, December to February as month of the year. And so you can kind of see the seasonality in the coastal current width, and the different colors are from 2016 to 2018. And what you may notice is that they kind of all gather around 15-kilometer width. And this is kind of what we would expect. You can calculate the width of the coastal current, and we expected that to be about 12 kilometers based on the basin configuration here and oceanographic calculations that were made by some of my physical oceanography collaborators. But what you'll notice is there's a reasonable amount of variability around this 15 kilometers. And reasons why we might have that are changes in influx of meltwater, diversion away from the ice front of the coastal current, widening and narrowing of the coastal current during storms can happen. And there's also potential errors in the technique with capturing the Antarctic coastal current width with thermal data. But it's really exciting to see that we can start to map this over multiple years and see some consistency that we would expect from oceanography using the thermal data. And so that sort of work is showing that we can combine the field observations with satellite imagery to really get a more robust understanding of the coastal current. We'll be doing that work in lots of different places around the Amundsen Sea and outside of it. This is super important to do because of how the Antarctic coastal current can impact heat transport towards the ice. So we're really excited to capture the coastal current variability in its location, especially for understanding this as ice shelves retreat away from the locations that they're currently at. Now, moving on, I'll talk to you a bit about how we can study various tiny features in it around all of Antarctica using the aid of machine learning now. This is in work that is done in collaboration with the International Thwaites Glacier Collaboration. And we're looking at, I'll explain to you in a moment what basal channels are and persistent planias, but we're understanding how these ice ocean features co-evolve with ice shelf stability. So kind of to tell you what basal channels and persistent planias are in case you aren't familiar. As I said, around Antarctica, you have warm water coming in at depth, creating a plume that rises towards the surface. Because that plume is turbulent, it entrains warm water into it as it rises. It also finds topographic highs in the bottom of the ice shelf and preferentially follows these. And so they follow the same path over and over and over again underneath the ice shelf. And because they're warm, they start to carve into the base of the ice shelf, which creates a basal channel. And the basal channel, you can kind of envision it as an upside down river that kind of funnels these plumes towards the ice front and up towards the surface. If the plume is buoyant enough, it will rise all the way to the surface. If it's not, it will exit out at depth. When it rises to the surface, it's carrying that heat. And so if you have sea ice that's forming on the ocean there at the ice front, it'll melt a hole, a circular hole in the sea ice and create a persistent plania. So that's just an open water area surrounded by sea ice. So you can see these persistent planias at the outlets of basal channels over multiple seasons, multiple years. And that's what we call persistence. It's a sensible heat plania. Now, because these are at the surface, we can detect them from satellite. We can start to potentially understand ice-ocean interactions happening beneath the base of the ice shelf from these features in places, obviously, that are really, really challenging to get to from ship and other instruments. So the work that we're doing is to understand how the variability in these might relate to changes happening beneath the ice shelf, basal melting and ocean stratification and things like that. So these planias are all around Antarctica. They're mostly located in areas where warm water reaches the base of the ice shelves much more consistently. And where we're focused into, again, is into the Amundsen Sea here at Pine Island and Thwaites Glacier. So this is Pine Island ice shelf. This is Pine Island Bay, the open water from satellite. This is a MODIS image. This is sea ice here floating on the ocean. This is all land ice around the base. We have a basal channel and we have a persistent plania that I'll zoom in on here. So you can actually see the basal channel, the surface depression associated with the basal channel. and the persistent polynyas there. So with Landsat, you can see it's a lot easier to capture these. The polynya is generally only about 1 kilometer across, so it's a very small feature. So we're used to looking at polynyas that are tens of kilometers across. And so these are tiny features that we really need Landsat to be able to study. So we're really wanting to investigate how the variability in these relates to mechanisms that are occurring beneath the ice. And to do that, we're automating the detection of these features in a cloud-based workflow. So we're building the cloud-based collaborative and reproducible workflow in AWS using Python and Jupyter. We have data ingest and structures. We have data processing, libraries, and visualization. Then we're using data from Landsat, MODIS, and also eventually Sentinel-3 to be able to study these. What we get from all of from this workflow is something like what we're showing here on the right, which is this is the polynya outlined. We want to be able to provide outlines of these features to the community, so people who study ocean color can use them in very easily. We want to be able to detect these and create these outlines as shapefiles, and to do that and automate this, we can also incorporate information about things like the basal channel, which is should be adjacent to these persistent polynyas, and the fact that the ice front is also adjacent there. So where these two places meet should be where persistent polynya is, and we can create a machine learning model that can incorporate all of this information. To start, I had a couple undergrads contributing to this. Ojin Lee is an undergrad at Columbia University. She did this very meticulous labeling of Landsat imagery in the area to capture polynyas. And Michael Field was an undergrad senior last year at Colorado School of Mines. He's now moved on to work with Mickey McKee in Florida. In geostatistics, he did a lot of work starting to build a machine learning algorithm that could detect the ice front in around Thwaites Glacier and Pine Island. And so this is some of the work that he's doing. And now since he's left, Ojin Lee is continuing to do that work. And that detection of the ice front can then be used and filtered into the physics-featurized segmenter that is being designed by Ellie Abrams. Ellie is a PhD student at Berkeley. She's a statistician and data scientist, and she's built this algorithm that incorporates the physics into the model in a way that makes sure that the model is taking into account the fact that we know some of the physics of this. So it doesn't make decisions like we're used to hearing about online where, the horse was detected based on the background or something like that. This really focuses in the algorithm on the physics that's important for making the decisions that we want it to make. So she's designing this right now, and it incorporates the work being done by Michael and Ojin to create this algorithm that detects the persistent polynyas. And from that, we can create a record that looks like this. So this is looking at that small polynya near Eastern Thwaites from 2013 to 2021. And the size of the circles tells you the aerial extent of this polynya. So just looking at the size of it through time. And there's a lot of seasonal and interannual variability that we can see with this. It's the largest in December. And this variability can tell us about potentially the basal melting that's happening beneath that. So we're working to integrate other data sets to show that basal melting and ocean stratification and these kinds of processes can be kind of teased out from this polynya, the characteristics that we observe at the polynya. So we can start to observe the polynya in an automated way. We've also done other work at the ICESat-2 Hack Week. If any of you are familiar, to look at how thermal and ICESat-2 surface elevation data can be integrated together. So ICESat-2 is a laser altimeter that captures the surface elevation of the planet. And in the ISAT2 Hack Week, the ISAT2 Hack Week is training for researchers at very many different levels to be able to use ISAT2 data and to share their knowledge. And then together, once we've provided a lot of code, we start to do projects together over the course of a week. So in about 3 days, the work that you're seeing here was put together by the five graduate students and myself that were on this project. So some of them had no experience using ISAT2, and some of them had very little experience using Python, but we did this work in the cloud and were able to collaborate very rapidly, start collaborating on this work and produce a project over the course of 3 days. So it's really cool work that we can kind of do in an educational way using the cloud in these hack weeks. On top of that, we're doing some data fusion and ground truthing with the different thermal products that we'll be creating or are already present. So Landsat's on the left, we have MODIS and Sentinel. We need to fuse that data in a way that allows us to integrate the temporal frequency and spatial, take advantage of the temporal frequency from MODIS and the spatial coverage from Landsat. So with this thermal data set, we can actually start to look at these features and ground truth them using seal tag data. So that and ship observations. So Elena Savage is a grad student at Colorado School of Mines who just actually had her paper accepted that shows that seal tag data, where seal tag data is gathered in wintertime, they can see that warm surface temperatures in the ocean data match up with the thermal anomalies that we see in Landsat and in MODIS. Landsat is at higher spatial resolution, so you can see the circulation a lot more clearly, but both are picking up these temperature anomalies, and we have been able to pinpoint that those are actually playing as warm plumes coming to the surface. So this is showing how we can use this data even across wintertime when there is no visible imagery to track these plumes. And that's really important because actually Landsat hasn't been gathering data in Antarctica in wintertime for most of the record. MODIS has. So we're really urging the Landsat science team to continue or to start gathering this data, which I think Ted Scambos and other people have finally brought to fruition. We will be capturing thermal data now in Antarctica, which is really exciting. So those are kind of all the projects that we're doing. This is these different pieces kind of fit together here, how I'm showing it. But what I want you to kind of notice here is I have over here on the right this box here showing that this is all done in the cloud in Jupyter Hub. And that allows us all to work together in a collaborative way. We can use GIS, or QGIS. We can use all of the same environments, things like that, to be able to collaborate in a much easier way. And so that's kind of what I want to end with here, where we're going next with big data. What's the future for glacier ocean research? And the project that we're working on to kind of understand some of that is called CryoCloud, where we're accelerating discovery for cryosphere communities using open cloud infrastructure. So before I dig into that project, I'll give you a little bit of background on open science. So NASA has declared that science done in a fundamentally more open way is the future. Open science is defined as a collaborative culture enabled by technology that empowers the open sharing of data, information, and knowledge within the scientific community, as well as the public, to accelerate research, scientific research and understanding. And so open science has been very recently at the forefront of NASA's agenda. They have created the Open Source Science Initiative, which aims to make science more transparent, accessible, inclusive, and reproducible. And within that umbrella, the Transformed Open Science program is working to lower boundaries of entry for historically excluded communities, and it's increasing opportunities for collaboration while promoting scientific innovation and the the goals, the aims of the Open Source Science Initiative. They've created a curriculum that helps teach scientists how to do this. That's called OpenCore, which you can find here if you want to check it out. So within that Open Source Science Initiative, NASA and now the entire US federal government, many federal agencies, and about 80 academic institutions have declared 2023 as the Year of Open Science. So that's meant to accelerate the push for open science and really get us moving over for the next 5 to 10 years that we're trying to make open source science more consistent throughout science and throughout NASA and the federal government. So one of the ways that we know that we can facilitate some of this open science is through cloud computing. So for anyone that's not familiar, the cloud is a place where you can have your data, your servers and infrastructure and your tools all in one place to speed up how the data computation and analysis. And this excludes anything that you need a router for that goes across the internet. All of this is in one place. And this means that we need the cloud, or the cloud is important and helpful at this moment because we're having this big data really flood into science. And as this data floods in, you're no longer able to download all of it onto your computer in a way that's useful. So instead, we can keep the data in the cloud on the internet. We can put our tools, make sure our tools are unique to the work that we do. They can be specialized, put that all in one place and rapidly do the computing without having to download. So that's the advantage of the cloud. And it really produces this place where we have a digital watering hole, a place where a lot of different people need data. They can access it in a way that that is accessible for lots of different kinds of communities and diverse communities. Disparate data sources can all be looked at in the same place. And it really allows us, by putting the tools and the data in the same location, it allows us to ultimately connect to society and impact critical decision-making on timescales we've never been able to do. And so with the cloud being a place where we can really innovate in open science, we started CryoCloud. And CryoCloud came about because of some work that I was doing with the ISAT-2 science team. So the science team meets twice a year, and last May, they had a cloud computing and open science panel where they talked about a lot of the concerns they had about open science and cloud computing. And some of those are that the cloud has non-intuitive pricing structures, computing options and infrastructure, the documentation is poor, it can be costly to use, you can easily ring up thousands of dollars without realizing it, the time to transition workflows it could be a problem, and it's not obviously more collaborative or faster to them. And myself and the other co-founder of CryoCloud, Joanna Milstein, who's a graduate student at MIT, really didn't agree with this viewpoint. This is not the experience that we had had in using the cloud. And part of that is because we worked with this cloud platform provider called 2I2C, the International Interactive Computing Collaboration. They built the platforms that we had worked on in the cloud and that really eliminated a lot of these issues and solved them. So we decided to collaborate with 2I2C to build a cloud computing platform with bumpers that cryosphere scientists could use to start to train and transition to cloud workflow. So it's a simple and cost-effective managed cloud environment. And we're also working within it to build best practices for our community to understand how we should be working in the cloud, what tools we really need, that sort of thing we're taking with user feedback. So this CryoCloud ends up being this infrastructure that's built and developed for cryosphere scientists by cloud engineers to make it possible to process data faster and democratize science. The CryoCloud should be persistent for at least 3 years. We provide small and medium instances for all users with the option of bringing your own AWS credits to have access to larger servers. We are developing new tools that will be built into the Jupyter Hub infrastructure because a lot of the developers, the 2I2C cloud engineers, are also developers for Jupyter. And we're also using community surveys and feedback and guidance to help 2I2C to scale up, because it's a relatively new nonprofit that's doing this work to really maximize cloud computing platforms for education and research. And so we're helping them to scale up with the work that we're doing too. So this is kind of what we've built for CryoCloud. If you want to check out cryonthecloud.com, that's where all of our resources are. The Jupyter book has training tutorials and information, and then the Jupyter Hub is the actual platform for cloud computing. We've been giving access to people and training through a lot of the cryosphere workshops that happen throughout this year. We'll be at WACE later this year, as well as AGU and some of the hack weeks. You can check out our GitHub. We have a CryoCloud Slack, community office hours, and we're bringing in related cryosphere communities to be able to share in the ideation and construction of new tools that we need. So we're working with Q Greenland to bring their infrastructure into the cloud and see if the cloud can really work with Q Greenland well. We're working with the Arctic Data Center to see if there's ways that we can access non-cloud data more easily from CryoCloud. So really building these tools that allow us to collaborate and communicate much more easily, and really build community within the projects that we have in the cryosphere. So what the cloud ends up looking like is over here on the left. This is a notebook on the Jupyter Hub that we have. This is one of our tutorials. It integrates opening data from ICESat-2, MODIS, and Landsat in using some of the tools like X-Array, IcePix, which is ICESat-2 tool, and Earth Access, which is NASA's data access tool. And we have a lot of the developers also in the same environment or similar environments, which means that when users have issues with these brand new tools that are being developed, they can provide feedback and submit issues very rapidly. And so it really accelerates the feedback and collaboration loops that we have. And so it accelerates how much research we can do and make sure that these tools that are being developed are developed with the researchers in mind who are meant to use them. It's all being done in one place. So now looking forward from this kind of cloud infrastructure that we have now and new ways of collaborating and communicating during our computing, what I really want to promote and leave you with are a few open science values that make this work really reach its full potential. So those values include intellectual generosity, intellectual humility, the right to participate in science, and that everyone deserves to be treated with dignity and respect. So I'll go through those really briefly. Intellectual generosity is the sharing of ideas and advancing others' understanding completely openly. This allows us to really reduce the scarcity model that we have, reduce redundancies and reinventing the wheel in order to accelerate the science that we're doing and really start creating, instead of competition where we're all building on the same pieces of knowledge at the same exact time, when we start to share a lot of our knowledge and communicate a lot more, we can build a ladder instead where we're all working on different pieces of this ladder and accelerate the process of getting to scientific solutions that we really want to get to. On top of that, we should really exercise intellectual humility. So while as PhDs, or masters, we have contributed to this, some very special knowledge to the body of knowledge. During the work, the PhDs that we're getting, the degrees that we're getting and afterwards, that work is very tiny in comparison to the body of knowledge that's out there. And our work really stands on the shoulders of giants. So as our contributions are small, having that intellectual humility will allow us to give and receive criticism with grace. And that allows us to find the gaps that we have, both in how we interact with each other and in the research that we're doing, find those gaps, have some humility in receiving or providing that, and really get at the big problems that we have in our fields. On top of that, I'd promote the right to participate in science. So that's democratizing science. That means that no matter what kind of computer you have, wherever you are in the world, if you have any kind of computer, if you have a little bit of internet connection, you can access science and data openly. And what this really helps us to do is increase impact by bringing science and data to local communities that have never had access in the past. And these are the places where we're really going to see a lot more impact from science. And last but not least, everyone deserves to be treated with dignity and respect. This goes along with diversity, equity, and inclusion. By inviting everyone in and treating everyone with dignity and respect, we start to improve the quality of the solutions we can provide to our science issues to answer some of these global problems a lot more efficiently. So with that, the open science values that I'm leaving you with, what I hope that you've taken from all of what I've talked about today, and from these open science values is one thing, that open science is a process and not a product. So this is a change in our culture and how we communicate and collaborate with each other that really helps to make our work more impactful. So with that, just to summarize, I've shown you how we can use field observations and satellite observations, fuse those together to better understand ocean circulation in Antarctica, new kinds of features that we haven't been able to study in this way before. We can answer these questions in different ways than we've ever been able to. We can use machine learning and collaborations with people who are in data science and outside to provide unprecedented opportunities for studying these small features around in continent size or across the continent in new ways we haven't been able to do before. And also with the big data that we have, that we can use the cloud and open science principles to really accelerate science to meet the global need. So with that, I want to thank you. You can contact me from any of the ways over here on the top right. I want to recognize our funding sources. Thank you so much.